The wheel, invented around 3500 BC, has a fatal physical flaw. Constant rotation against rough earth grinds down the wood. A single large rock chips away the rim, making the wheel permanently uneven and destroying an expensive central piece of technology. The solution was an expendable layer. Instead of replacing the entire wheel every time it took damage, you wrap it in a protective barrier that takes the beating, wears down, and can be swapped out cheaply. By the time we were building wooden wagons, wheelwrights were forging thick steel bands. They would heat the metal to expand it, slip it over the wooden wheel, and then quench it in water so the steel contracted into a tight, permanent grip. It worked, but it was brutal. Steel offers zero shock absorption, translating every bump directly into the spine of the passenger. And if a heavy load bent the metal, that single kink required prying the entire tire off and starting over. Human expansion across rugged frontiers, like the taming of the American West, relied entirely on this highly durable, fiercely uncomfortable technology. We needed a softer ride. In 1888, a Scottish veterinarian in Belfast named John Boyd Dunlop was listening to his son complain about how harshly his bicycle rode on solid rubber wheels. Dunlop wrapped the wheels in a rubber tube and filled it with air. He created the first successful pneumatic, or air-filled, tire. Because the pressurized air absorbed impact rather than fighting it, Dunlop's invention immediately dominated local bicycle races, leaving solid wheels in the dust. By the 1920s, engineers were synthesizing artificial rubber to meet automotive demand. The standard became the bias ply tire. It featured two main parts: a pressurized inner tube holding the air, protected by an outer casing made of overlapping fabric layers called plies. Following World War II, Michelin refined this architecture. Instead of crisscrossing the fabric layers, they laid them perpendicular to the direction of travel. This radial tire flexed better, gripped the road tighter, and lasted much longer, becoming the undisputed global standard by the 1970s. Over a few short decades, the tire evolved from a crude, bone-rattling iron ring into a highly engineered, pressurized structural component. As global demand for radial tires exploded, new manufacturing hubs emerged. In 1941, the Chosun Tire Company was established in Korea, standing up early industrial machinery to meet the needs of a rapidly modernizing economy. Preparing for a major international push in 1968, the company rebranded to Hankook Tire Manufacturing. Hankook literally translates to Korea, stamping their geographic identity onto their expanding global export lines. This chart shows current global tire sales, ranking Hankook as the seventh largest manufacturer in the world. To maintain that position, their modern facilities produce more than 102 million tires every single year. Pushing that volume requires massive infrastructure. Hankook centralizes their R&D at a high-tech hub called the Technodome, and they test those designs at the Techno Ring, Asia's longest tire test track, spanning 1.26 million square meters. Modern tires are complex technological platforms. To survive at the top tier of manufacturing, a company has to test synthetic rubber blends and tread geometries under the most extreme physical conditions imaginable. Electric vehicles are a major engineering challenge. Their massive battery packs make them significantly heavier than combustion cars, placing extreme stress on the rubber. Hankook's EV contour technology alters the internal structure, increasing lateral rigidity by 25% to prevent sidewall roll during sharp turns. They also tackle cabin noise. Their OptiPitch feature adjusts the size and sequence of the individual rubber blocks on the tread. Spacing them precisely disrupts sound waves and quiets the hum of the road. For wet weather, engineers cut tiny, specific channels into the shoulder blocks called water pipe kerfs, along with zigzagging 3D sipes. These microscopic slits act like microscopic pumps, instantly draining water away from the contact patch so the rubber can grip the asphalt. Hankook refines these tolerances on the track, serving as the official tire for both the World Rally Championship and Formula E electric racing. Modern mobility is an exercise in microscopic engineering. A fraction of a millimeter in a tread block dictates top speed on a track and hydroplaning safety on the highway. North America represents a massive percentage of global tire demand. Rather than shipping millions of heavy rubber units across the Pacific, Hankook made a strategic shift to build the product where it's driven. In 2016, the company planted a firm flag in the U.S., relocating its entire North American corporate headquarters to Nashville, Tennessee. A year later, they followed that up with a staggering $800 million investment, opening their first state-of-the-art American manufacturing plant in Clarksville. Establishing a massive domestic footprint allows Hankook to engineer, build, and deliver their mobility solutions straight into the American supply chain. The NHTSA pushes a simple rule: tires are the single point of physical contact with the pavement. Every U.S. tire undergoes the Uniform Tire Quality Grading System, rigorously measuring tread wear, traction, and temperature resistance to pass extreme friction tests. We started with crude, heavy iron rings that literally shook wagons apart and required a blacksmith to manually fix. Today, we rely on chemically synthesized pressurized radials shaped by supercomputers. Engineered on test tracks and manufactured right here in the U.S., the modern tire remains our most vital, life-saving piece of expendable technology.